All right, good evening, everybody. Let's go ahead and get started. As usual, I'll start by bringing up the syllabus, and here we are in week 4. We've got a busy night tonight, 3 different topics we're going to talk about, 3 different chapters. Obviously, we're going to take a pretty high overview, right, to hit these three chapters in the amount of time that we've got, and then it'll be the last one on test doubles. Excuse me. That will be the major part of our class exercise tonight. So the next assignment, it should be posted now, or maybe I set it up to post at the end of class tonight. But that will be due in 2 weeks. That assignment will be based on the class exercises tonight. And I think that's about it for the syllabus. So now that more people are here, we did have a discussion earlier on about how to submit the assignments. And your group, however many people that is, you just need to submit it once. So just pick one of you and submit it, and have a list in there somewhere of, you know, all the people that were all the people that contributed to it. If you're in a group and you've already submitted, oh, hey, there were 3 of us and we each submitted it separately, that's not really a problem. But just send Ridwan, our TA, an email and let him know, hey, the 3 of us, we're all in the group, we posted the same thing. And that'll just make his life a little bit easier when he's trying to grade things. All right, so let's look at this past week's quiz. Scores were overall quite good on last week's quiz. So good job on that. And kind of a quick look at some of the questions involved. As usual, there were multiple questions. One of them was this dual priority queue, where we queue things, we put things into the queue, they can be high priority or low priority. And then when we pull things out of the queue should dequeue them to us in FIFO order. So first in, first out order, except that all of the high priority things will dequeue before any of the low priority things. The alternate question to this was a dual priority stack. Not very different. I just wasn't feeling that clever. Basically, all exactly the same, except that instead of a queue, a stack obviously returns things in LIFO, last in, first out order. But otherwise, all the concepts are the same. I'm just going to talk about the dual priority queue tonight. So what does our test look like? If we're trying to write a test for this dual priority queue, we're doing this still kind of following that intuitive process of, you know, thinking about in general, what does this thing do? What are the requirements or the stated functionality that was given to us? And what would be appropriate things to test based on that functionality? So some things that I might want to think about, or you might want to think about in testing this particular class. Well, we'd like to think that, okay, all queued high priority items are dequeued before any low priority items. So that suggests that maybe we'll queue things in a mixed priority order and verify that when we dequeue them, we get them back in high priority and low priority order, right? All the high priorities first, and then all the low priorities. We also know that all items with the same priority are dequeued in a first in, first out order. So that seems like we should maybe write some tests or incorporate into our tests. Well, we've queued up 2 things that are high priority, and we want to make sure they come back in the expected order. We might also have assertions for the low priorities to make sure the low priorities also come out in the correct order. Like that. The dequeue method returns null if the queue is empty. So we should probably check that. We could do it at the beginning or at the end or both. If we try to dequeue something at the beginning, it should return null. And if we dequeue something at the end, that should also return null. Now, is there a difference between doing it at the beginning and doing it at the end? Not really. My thinking here was, if we've just created the queue, it would be nice to verify that the queue is empty. And after we're done dequeuing all the things that we put in the queue, right? We queued up 4 things, we dequeued 4 things. Well, it would be nice to do another check at the end to make sure that the queue is now actually empty, that things were actually properly taken out of the queue. So that's why in my example, I have it at both the beginning and the end. Again, if you had the dual priority stack question instead of the queue question, it's really all the same thing, except that the order of the high priorities, the order of popping the high priorities and the order of popping the low priorities would be reversed, right? Because it's last in, first out instead of first in, first out. So then we had some cucumber tests. You're responsible for the system test for a microwave oven. And one of the questions was, write a test to ensure the customer safety, right? Ensure the customer stays safe when the customer starts the timer or starts the microwave oven with the door open. I have a question here in the chat. Would it be okay if tests were split into separate methods? So I think by that we're, it's hard to go back. Here we go. So I think you're suggesting, well, you just had more than one test method. More than one test method is fine. So it can be split up any way you want. Although if you queued up all highs in one method and all lows in the other method, then you wouldn't have an opportunity to check that they actually dequeue in priority order. But assuming that you've got some implementation that checks all these things that the queue or the stack is supposed to do, then exactly how you arranged it is really up to you. All right, so let's get back to our microwave oven. We've got a test where the customer starts the timer with the door open. You can certainly have variations on this, but a pretty straightforward result here would be, given that the door is open and the magnetron being the part of the microwave that actually generates the microwave radiation, is off, and optionally that the timer is stopped. When the timer is started or the microwave is somehow turned on, then the magnetron is off or remains off or turns off or something like that. And optionally, perhaps the timer is stopped. I don't really care about the timer that much. The timer isn't necessary for keeping the customer safe. What is necessary is that the customer tried to start it with the door open and it didn't start. And then the related question to this is kind of the opposite safety case. What about if the microwave oven is running and the customer opens the door? So that would look something like, given that the magnetron is on or that the microwave is running or something else like that, and the door is closed, those are the preconditions. Then when the door is open, then the magnetron is off or turns off. So Kyle, I got a question here in the chat. For specific answers to the quiz, I'm going to direct you to Ridwan. So check in with him, and the grading should all be clear, reasonably clear anyway. There should be grading comments in the quiz, and if that's not clear, then check in with him as he did the grading. Thanks. All right, so that's what Cucumber looks like. That's pretty much it for Cucumber and system level tests. I won't promise that nothing like this might be on the final, right? I mean, you could easily have a short question like this on the final exam, because that is, of course, cumulative for the whole semester. Otherwise, we're kind of taking this Cucumber system testing and we're putting it behind us at this point. So where are we in the House Cup? Well, the Muggles have been playing a strong game here this semester. Couple of slide clarifications, a couple of first submitted things. Ravenclaws have really done a little bit of catching up here. I think that Ravenclaw team, I think, had the highest the highest quiz grade. I think there were actually 2 people that had the highest quiz grade, and they were both Ravenclaw. So well done. Still anybody's game. All right. So with that, let's go
Professor, I had one
ahead.
suggestion.
Sure. Yeah.
I was wondering if we can make the quizzes 45 minutes instead of 30 minutes. That way we're not rushing and panicking and looking at the timer as often.
I'll take a second look at the quizzes. You know, the part of the let me give you a very straightforward background on why the quizzes are the way they are. There are a lot of things that instructors have tried to do or talked about doing in order to prevent cheating on online quizzes. I don't know if any of your classes have, you know, the lockdown browser. I've read articles about people. I'm not aware of this at GMU about, you know, you have to take the quiz with your camera on. I actually think that all of that is pretty ridiculous. You know, making you take a quiz with a lockdown browser that you can't use for anything else. Well, you know, raise your hand if you have one internet device, right? Right, everybody's got a phone or an iPad or multiple computers, right? All of those things are a waste of time. And so I pretty much have just taken the position, it's going to be open book, it's going to be open notes, it's going to be open all resources, but you kind of have to know what you're doing, because while you're going to have time to look something up, the object is you're not going to have time to look everything up. That's why there's a time limit on the quiz. That said, I will go back and take a look at, actually, I think what I'll do is I'll look at the statistics. I can actually look at the quizzes, see how long everybody's been taking on the quizzes, and I'll be happy to make an adjustment to the quiz length if the overall statistics suggest that that's the right thing to do. How's that?
That sounds really fair. I really appreciate it.
Great. So thank you for bringing that up. I'm, you know, I don't want to, you know, as I said the first week, my objective is not to make this a punishing class. My objective is to have you come out of the class having fairly learned the things that you need to learn. So, all right, with that, let's launch into our topics for tonight. We're going to start with Chapter 4, Agile Testing. So traditional testing, or traditionally, testing has largely been driven by a lot of upfront analysis, a lot of modeling, because we know that it's less expensive to find and fix problems the earlier we are in the software lifecycle. I've shown this graph or a version of this graph before, and basically, if you find something, if you find a problem in requirements phase, it's easy, cheap and easy to fix. In design phase, it's, I don't know that this line is really flat, but still, design and even coding, it's relatively easy to fix a problem. But as we then get into later stages of testing, especially when we get, now we've distributed this thing, it's in operational use, we have customers using it, and now we have to fix a problem, right? Now we're talking really expensive. We're talking, I don't know, maybe a vehicle recall, right? We have to have everybody bring their, you know, 2021 F-150s back into the shop for a software upgrade, right? This is incredibly expensive. So analysis and modeling and all that heavy front end work actually can identify potential problems early in development. It does work, assuming that the requirements are complete and that they don't change over the course of the program. And experience has shown, how often does that happen? Almost never, right? We have program development lifetimes that are, even for relatively small things, they're usually many months. For large things, you know, large accounting systems, Department of Defense systems, it may be 5 years. And during 5 years, things change. The customer's ideas of what they want change. You're halfway through and they come back and you say, you know, I actually wanted to do something else completely. All those things that it does, but also all these other things, except I want some of the things that it does to do different. So these things are always changing. And if you're doing this waterfall model, right, we do all the analysis, we do all the architecture, we do all the design, we do all the coding, things are changing out from underneath you. And if you're going to go back to the beginning every time something changes, then you may never actually finish. And you don't have to read very far into the news, especially if you look at major years-long defense procurements, to find programs that spent millions or hundreds of millions of dollars and never completed, because not necessarily because the people doing it weren't smart or weren't good, and they certainly weren't trying to, rip the government off, but the ground under their feet was changing faster than they could change the project to adapt to it. So that waterfall model of software is pretty much understood to be broken at this point. So how do we write good code? And I'll give you a moment to appreciate this one. So we're stuck down here with, I don't really know how we get there. So let's talk a little bit about maybe ways that we can get there. And all of this is kind of true, but there's maybe a different path through here that's a little bit better than the two that I mentioned. So when we're doing agile development or using agile methods, we're starting off by understanding or taking for granted or accepting the fact that engineers and customers are not really good at developing requirements, right? We don't anticipate the things that are going to change, and we don't often need the things that we anticipate will change. So requirements can get out of date quickly. They may be changing on a continuous or near continuous basis. And we're not good at this, right? We're not good at predicting what is this system going to look like in 4 years when we're done. And even if we were good at predicting it, we learn things as we go, right? As developers, we learn things as we go, and the customers that we're interacting with learn things as we go. And so why shouldn't we use that knowledge to make a better system, right? If we show the customer something halfway through and they go, yeah, that does exactly what I want, but now that I see it, it would be better if something, right? Well, why shouldn't we do that, right? Why shouldn't we make the system better? We should. So how are we going to do that? Well, generally speaking, in agile development, we're going to start small. We're going to evolve our system over time, kind of incrementally repeating all the requirements analysis in little pieces as we go. So agilemanifesto.org, you can go to this website and see the original Agile Manifesto. The original Agile Manifesto, oh boy, if anybody knows, tell me, but it's probably 20 years old now. I mean, this is not new. A group of very prominent software developers, I guess I'll say, kind of got together at a summit to talk about what's wrong with software development. And this Agile Manifesto was kind of what they produced as a result. And they came to value individuals and interactions, right? The people and the interactions between those people as more important than processes and tools. And they came to value working software as more important than comprehensive documentation, and working with your customer as more important than contract negotiations, and responding to change as more important than following a plan. Those things on the right, processes, documentation, contracts, plans, they are not bad. They have value. But the point of the Agile Manifesto is that the things on the left have more value. We could have a long debate over the beverage of your choice about the Agile Manifesto and whether it works for everyone in the world or whether it just works if you're a world-class software developer. But there are certainly some nuggets of usefulness in there. The bonus double cartoon issue. We're just going to start writing code and complaining. You got to love Dilbert. All right, so when we're doing Agile development, the first thing we need to do is we need to change our definition, or change how we consider correctness, or what we consider correctness to be. Traditionally, we're looking for some kind of universal correctness, and I don't take this graph too literally. Basically, we're just saying that we consider the system correct if for all possible values of inputs, this property holds true. That, of course, is hard to prove. When we go to Agile development, we move from this universal definition of correctness to an existential definition of correctness, basically saying, here's a set of tests. If this set of tests is satisfied, then our system is correct. Now, we've put the pressure on the test set, right, to be as effective as it needs to be, but we now have a test harness, right, a set of tests that is our guardian of correctness. If all of the tests pass, then we consider our software to be correct. That is a lot easier to prove than for all possible inputs, this condition holds. So Agile methods like this work best when we can run those tests against the current version of the software at any time. And ideally, run the tests against the current version of the software all the time, continuously. Typically, that's interpreted as anytime someone makes a change, right? Whenever we make a change, we run all of the tests on all of the software, or at least on all the software that has changed. That lets us catch mistakes or changes early. Now, those changes, right, if I change a piece of software and a test fails that used to pass, we do have to ask ourselves, does that mean that the software is wrong? Or does that mean that the test is no longer correct? And we need to go back as engineers and consider that. It's not always that the software that I just changed is wrong, because if I change the behavior of the software, that could easily change how it performs on a test. So what we'd really like to do is take a continuous integration server like Jenkins, Jenkins is the most common one that I see. Bamboo is another one from Atlassian. There are others that basically will automatically detect when someone has checked in new code, build everything, run the set of tests, and let us know what the current status right now of the system is. And the key thing here is that continuous integration system, it's not just running the tests. Because the tests define correctness, it is constantly telling us whether our system is currently correct by the definition that we've given it in tests. So doing things like this reduces a lot of risk. So here on this chart, we've got time here on the x-axis, and basically changes that we haven't fully brought into the system, right? Changes, things that we're working on the y-axis. Traditionally, this red line will work lots and lots and lots and lots of changes, and then we'll do a big integration effort and say, okay, let's get all these changes all working again and get us back to a fully working system. Well, we actually take on a lot of risk by doing that. The more changes we've made, the more likely it is that somebody on the team is going to make a change, but something else has also changed that's going to break their change, right? So the more people that are working on the same software at the same time, the more likely it is that they're going to be interfering with each other. So if we're using continuous integration, we're making very small changes and much more frequently integrating those changes, typically every day, maybe even faster than that. So we are never very far away from a working system. If I have a continuous integration system running, let's say nightly, all of my tests run every night, I know I'm never more than one day away from a working system. Because if my tests pass today and they fail tomorrow, well, why did they fail? Well, it had to be what I did in the last one day. It's not that hard to go back and figure out what you changed yesterday. All right, so we're never very far from a working system. So that brings us to test-driven development. When I was doing my, I guess early in my PhD, Paul Ammann ran basically a special topics class on test-driven development, research into test-driven development. That was a really interesting class, and I enjoyed that. Test-driven development, it's a method for developing software where we actually build the test first. And this seems strange. You're probably thinking, well, how can I build the test before I've built the software that I'm running the test on? Because the test has nothing to talk to. Well, actually, we write the test and then we write just enough of the software so that we can run the test. And then we make sure that the test fails, right? Because I didn't write any functionality yet. I just wrote a function header, right? I just gave the test something to call. And the test fails. That's kind of a sanity check that the test is really testing that we did something, right? And of course, at first, we haven't done anything, so the test fails. Then I write just enough code to make the test pass. And then I move on to my next test. And the core principle here is whatever functionality you're thinking, you're probably not going to need it. So only build the minimum software that you need. And that satisfies a couple of problems. First, it reduces your software size. It reduces your scope creep, right? You're building only the functionality that you need. The less software you have, the fewer faults you have in it. The less software you have, the fewer security vulnerabilities you have in it. So this keeps us building basically very lean, mean software, the minimal amount of functionality that we need to get the job done. And so the process for test-driven development pretty much looks like this. I identify some feature, right? Some small thing that my software is supposed to do. I write my unit test for it. I run the unit test. Does the test fail? Well, if the test doesn't fail, then I must have a problem with the test because I'm not running it against anything yet. So the test should fail. If it doesn't, then I need to go back and reconsider what I did in the test. If it does fail, which is what I want at this point, then I move on and I implement some code and I write just enough code to make the test pass. If the test doesn't pass, I go back, I fix it until the test does pass. Then I come up here and I refactor my code. When I'm writing code down here in this phase, I'm doing it quick and dirty, right? This is quick, dirty, possibly ugly code. I'm just trying to get this test to pass. Now that I have that test passing, I can come and I can refactor the code. This is basically where I'm doing a code cleanup. Oh, I have a duplicate code here, here, and here. I should pull that out and put it in a private method. What other cleanups can I make? Now's a good time to maybe document the code a little bit. And then I can rerun all my tests. And I know that I can refactor with very little fear, right? Because if I make a mistake refactoring, if I break it, then my tests are going to tell me that I broke it. So I can do this refactoring without too much fear. And then I can decide, do I have enough tests yet for this feature? Now, this is a place where we could apply test criteria, like perhaps, have I executed all the lines of code? Or other test criteria that we'll talk about later in the semester. If I don't have enough tests yet, I can go back, I can write another test, make sure it fails, implement the code to get it to pass, refactor everything again until I get to the point where I have a sufficient number of tests for this feature. And then I'm done with this feature. And then I can go pick up the next feature. What else is this code supposed to do? And I can start the process again for that. So I mentioned refactoring a little bit. What is refactoring? If you're not familiar with this term, it's a very important definition. When I'm refactoring, I'm improving the internal implementation while retaining the external behavior. So the function calls all look the same. Any API, programming interface, the interfaces all look the same. To anybody on the outside, everything looks the same and behaves the same. But my internal implementation has improved. It's gotten cleaner, more maintainable, perhaps faster, right? Maybe less error prone. So why do I want to refactor? Well, I'm going to improve things like my code size, right? I want to make my code size smaller, less duplication, improve my maintainability, maybe improve my performance. If you're familiar with these terms, it's going to reduce, there's an agile term called code smells, where, okay, this code works, but you know, it's kind of ugly, and this is the kind of code that's going to be a problem later. Or technical debt. Technical debt is places where, okay, I took a shortcut here. I know that this shortcut has limitations. I know that this is possibly going to cause us some problems later, but I wanted to get this code running right now. And I'm willing to take on the debt of getting this code running right now, knowing that I'm going to have some cleanups later. Well, refactoring is a good opportunity to work on those cleanups. We can also take the same test-driven development approach and use it at a higher level, like at the system level. So when I'm using acceptance test-driven development, it's basically the same thing, but at a higher level. I'm going to write an acceptance test, like those cucumber tests that we were talking about last week, before I develop the software. Okay, well, that again seems weird. How can I write a system level test before I have a system to run it against? But the key here is that the system test defines the acceptable behavior of the system. It is the system's functional requirements in a form that's very easy for developers to understand and in a form that is provable, right? If this test is the system's functional requirements and I can write code to make the system pass, to make the test pass, then I have satisfied the requirement. And this really, it looks very much the same, right? So I'll take a user story, some high level requirement. I'm going to write some acceptance test like that gherkin test when the microwave is running and the customer opens the door, the microwave shuts off. And then I will write code using test-driven development until I've satisfied everything that needs to be done for that high-level test. And then I have a passing system test or a passing acceptance test. So we often run into a problem in practice where we have a lot of legacy software, and much, maybe most of all of the software that's out there is legacy software. What is legacy software? Legacy software perhaps has out-of-date tests, or maybe it has no tests. Legacy software has poor requirements or outdated requirements, or maybe no requirements. It probably does not have design documentation. It probably does not have institutional knowledge anymore. Oh, Sarah wrote that, you know, 5 years ago. Oh yeah, she left the company 4 years ago. Yeah, we don't know what that code does. We use it. Yeah, don't touch that. It's too dangerous to touch. Nobody understands it. Don't touch it. So companies obviously often choose not to change legacy software because we're not sure what it does. We're not sure how it works. It doesn't have tests. If I touch it, how do I know that I didn't break it? And really, when you've got lots of legacy software and you may have millions of lines, you can't just stop everything and let's go write tests on millions of lines of software. You can't do that. That's just not practical. So we can't write tests for it, but we also kind of need it, and we have to keep making progress on the system we're working on. So what can we actually do? Well, we can basically take an approach called incremental test-driven development. And so when we need to make a change to a piece of legacy software, we'll use a TDD approach, but just for that little piece, not for everything. So if I'm looking to change one function in this legacy software, I'm going to write a few tests that show how the software behaves now, right? I'm going to make those tests, and those tests should pass. And then I'm going to change the tests to demonstrate the new behavior that I want. those tests should fail, or at least some of them. And then I'm going to modify the legacy code, this little piece of the legacy code, in order to make those tests pass. So now I've got 1 million lines of legacy code that had no tests, and now 999,000 lines have no tests, but I've got tests for this little piece. Well, that's better than I was yesterday. And as the project continues over time, we're going to accumulate more and more tests. And eventually, you know, a significant part of that legacy software will end up with tests. And so I've made a real improvement in my overall system. I haven't solved the whole world, but I made an improvement in some small areas. There are some possible shortfalls, right, or shortcomings or limitations of using test-driven development or acceptance test-driven development. We need to ask ourselves, do tests that come out of that process test the software thoroughly? So do they achieve good coverage? Well, probably. If I'm doing test-driven development and I'm writing only enough code to make the test pass, then I probably don't have a lot of extra code that isn't needed by the test. But do the tests find most of the faults? And if those tests pass, should I be confident that the software is reliable? And maybe not, because most Agile tests focus on, the usual term is happy paths, right? A happy path through the code is a normal use case. This is what it looks like when everything goes right. And that's how most developers write their TDD tests. They test the normal things. Well, what I expect to happen is this, but those tests might miss things that confused users might do. If I'm not sure what to input next or what buttons to select next, I may cause something to happen that the testers did not anticipate. If I'm a creative user, I'm just trying to make the system do a little more than what I know that it does. Or especially if I'm a malicious user, right? If I'm trying to hack into this system or compromise this system in some way, I'm not going to be focusing on happy paths. I'm not going to be focusing on providing the system with normal data. I'm going to be focusing on providing it with abnormal data to see if I can get the system to crash or to do something that I want it to do, that the developer didn't want it to do. And these Agile tests may not deal with those situations very well. So how do we design better tests? Well, we can take a human-based approach. We can create additional user stories that describe those exceptional paths. For example, I might, if I was writing code for a checking account, I might write a test to say that if there's $100 in the checking account and we write a $50 check, then there should be $50 in the checking account. But an exceptional case might be, well, what if there's $100 in the account and I write a $200 check? What should happen then? So writing those additional tests sometimes takes some domain expertise. It's an intuitive process that's a little hard to teach. It's also really hard to know when you're finished. These can be valuable tests, but it's hard to do all of your tests this way. We can also use modeling and coverage criteria to do this. We can model the input domain, or we can model the software behavior. This is a discrete process. It's got some built-in notions of completion. So for example, if my goal is to achieve statement coverage, well, I know I'm complete when I've executed every statement of the program. We could debate whether statement coverage is the right thing to pick, but if we pick that, I know when I'm done and I know how close to done I am. Turns out that these two together can actually provide really good overall testing, because human-based approach has shortcomings, model-based approach has shortcomings, but they kind of have opposite shortcomings. So used together, we can, we can kind of fill in those gaps. And modeling and criteria, this is really all of part 2 of the textbook that we start next week. So the rest of the semester from here will largely be talking about modeling and criteria for testing. All right, that takes us to the end of our Agile programming overview. What are the important things to remember here? In Agile development, we're assuming that requirements and things are changing. We are using the test set as the oracle, right? The test set tells us whether our system is correct. Those are probably the two most important things out of this. All right, so questions here. All right, let's take a quick look at criteria-based test design. As I mentioned, the rest of the semester, starting next week, is all about particular criteria. Criteria.
I have a question.
Sure.
In slide 8, where you convert the like the traditional domain to the agile approach.
Yes.
So is this including like all for all x greater than or equal than y, or does it include a negative number as well?
So that, I would say, is a detail that doesn't really matter, because this was really just intended to be an example of, in traditional testing, you're trying to make statements that always hold true, right? So for all x and y, that x is greater than or equal to y. That's just a little trivial example of something that might be, we always want this to be true, right? But if you look at it in the sense of, you know, of a real system, you might be saying things like, for all possible, you know, for all possible login strings, you know, the system will only accept a login string that hashes to a particular value. So, okay, that's a general statement. How do I prove that that statement is true? I can't write every possible string, right? So I don't have a way to prove that that is true. I could potentially disprove it. If I could come up with a counterexample, I could disprove it, but I can't prove it. So we're going to recognize that I can't prove that the software is always correct, whatever it is the software is doing. So instead, I'm going to create a set of tests. And I'm going to say, well, if this set of tests is satisfied, then I accept that my system is working the way it's supposed to work. Right? So I'm taking the definition of system correctness away from some broad general statement, and I'm moving my definition of correctness into this set of tests. Now it's up to me to make a set of tests that's adequate to show that the system really behaves the way I want it to. And even if I had these 5 tests and they all work, there's always a possibility that there's another test that wouldn't work. All right, so I have to be careful in what I'm selecting in my tests, but we're basically saying if the set of tests passes, then I consider my system to have the correct behavior. So is that clear? It's not really about this x is greater than or equal to y. It's about making broad statements that some things are always true. And we're recognizing we can't prove that things are always true, but I can prove that this particular set of things is true or behaves the way I expect.
I see. Thank you, Doctor.
Okay, you're welcome. All right, so let's dive into criteria-based test design. So we've seen this graph a couple of times, or this image a couple of times. We've talked about how that waterfall model of following our way down the left side and back up the right side, you know, isn't really what we want to be doing anymore, right? That's not Agile. And the old view is that every one of these verification processes is different than the rest. Unit testing, that's a different thing than module testing, and that's a different thing than integration testing, and that's a different thing from system testing. But when we're looking at test criteria and our model-driven approach, we have to ask ourselves, well, are they really that different at all? And if we take a new view and say, well, our testing view is based on some kind of structure, right? Some model of the system and some set of criteria that we want to apply to the system. Then we find that our test design is largely the same at each phase. Whether I'm doing unit testing or I'm doing acceptance testing, my process is largely the same. I'm going to create a different model. Right, the model of the system that I create at the unit test phase might be, the lines of code or a control flow graph that shows all of the branches in that piece of code. That might be the model that I make. Whereas at the system level, right, at the acceptance testing level, my model might be, well, I care about, what are all the possible things that someone could type in, right? What are all the possible inputs that could come into the system, right? So creating the model is different. And picking my test values is different. Automating the test might be very different, right? In unit testing, I'm doing JUnit. In acceptance testing, I might be using Cucumber. I might be using some other tool that, works with my GUI and picks boxes and buttons on the GUI and sees what the GUI does, right? There are tools that can do that. So the automation might be very different, but the process that I'm going through is actually very similar. So as a tester, my job is simple, not so simple, but simple, right? In concept, I'm going to define a model of the software, and then I'm going to find ways to cover that model, to satisfy that model, right? So how I'm going to satisfy the model depends on what kind of model it is. And coverage matters, because the more coverage we have, the more confidence we have in our system's correctness, and the more confidence we have that we've reduced our maintenance cost. So we've talked about these definitions before. Let's just touch on them again. We can have a test criterion. A test criterion is a collection of rules and a process that we can use to define our test requirements. And our test requirements in turn are specific things that have to be satisfied for our testing. So where are we here? We're going to be using test criteria, right? We're going to build our model and we're going to be applying test criteria, and that's going to give us our test requirements. And then later we'll take our test requirements and turn them into test cases and execute them. But right now we're going to be applying those criteria to build our test requirements. So there are lots and lots of different types of test criteria out there. Arguably, they are based on 4 different kinds of structures. We can be thinking about input domains, right? What are the possible inputs that can come into our system? We can be thinking about graph-based models. We can think about logic-based models, and we can think about syntax-based models or descriptions. And we will look at each of these 4 over the course of the semester. So where am I going to get that model? Where do I get that structure from? And I can get that from a lot of different artifacts. So for example, if I want to do graph-based models, I can get graphs from a lot of places. Perhaps the most obvious place to get a graph is from the source code, right? I can take the source code, I can turn it into a control flow graph. It's a very common thing to do. And then I can start looking at how do I cover that graph. If I have a state machine, well, state machine is already a graph. So it's really easy to apply graph-based criteria to state machines. But I can also come up with graphs from UML test cases, from requirements documents, from other places. If I want to build a logical model, I can extract that from decisions in source code, obviously, but also from conditions in use cases, right? What are the cases? What are the conditions that will drive this use case to occur? if I have a finite state machine, what are the guards or the conditions on the state machine transitions? Those are places where I can find logical expressions. So we've talked about coverage. What does coverage mean? So we're going to have, you know, I'm not a big formal definitions person, but we have to have some in order to make any progress. So let's go ahead and define coverage. So if I have a set of test requirements, TR, and I have some coverage criterion C, then a test set T satisfies coverage for that criterion if and only if for every test requirement in the set of test requirements, there's at least one test in the set of tests such that that test satisfies the test requirements. I find that to be a formal and really wordy way of saying there has to be a test, right? Every test requirement has to be satisfied by a test. And if it is, then I've covered that criterion. So there are some exceptions, right? Because there can be infeasible test requirements. Infeasible test requirements are test requirements that cannot be satisfied by any test. So possibly there is no possible test case that will meet that test requirement. How can that happen? Well, for example, we might have dead code in our program. Dead code actually happens fairly often. So we might have a structure that says, if A is greater than or equal to B, do this. Else if A is less than B, do this. Else do that. Well, there is no possible else, right? A is either greater than or equal to B or it's less than B. There are no other choices. So I could never have a test that would execute that else case. That else case is dead code. So that's a pretty obvious thing. You could look at that code and go, wait, I can never get here. But in general, detecting infeasible test cases is undecidable for most test criteria. So we can never be completely sure that there are no infeasible test cases. So we have to understand that we can have test requirements that may not be able to be satisfied. And that's okay if we can show that they are infeasible. As a result of these infeasible test cases, achieving 100% coverage is often not just hard, but impossible. So if I had a piece of code that had that little bit of dead code in it, and I had chosen statement coverage as my criterion, I cannot achieve 100% statement coverage because I cannot execute whatever's in that else. Doesn't matter what test I write, it just can't be done. What should I do? Well, I could either accept a lower amount of test coverage and maybe document, oh, this is why I couldn't get to 100% because we couldn't run that. Or maybe we go back and we change the artifact and get rid of that else, or take it out since it's dead code. There's different ways that I might deal with it. But given any particular model, it may not be possible to achieve 100% coverage. Which brings us to, cartoon number 30 for today. Cartoons give me a great chance to take a drink of water. I think between XKCD and Dilbert, I think every possible technical situation has been covered in a cartoon. So we've achieved cartoon coverage. All right, let's take a look at applying two different coverage criteria. What does it mean for us? What are the things we need to think about? So we're going to do a little bit of work with jelly beans. So for jelly bean coverage, we've got 6 flavors. These flavors are a little weird, but they're less weird than Paul Amann and Jeff Offit's flavors were. We've got lemon, we've got lime, we've got mango, banana, tangerine, and pineapple. And we've got 4 colors of jelly beans in our bag of jelly beans, ignoring some of these colors. We've got yellow jelly beans, right? The pineapple and the lemon are yellow. We've got green jelly beans, lime. We've got orange jelly beans, mango and tangerine. We've got white jelly beans, that's the banana. So what are some possible jelly bean coverage criteria? We could have a flavor criteria. In order to test these jelly beans, we need to taste one jelly bean of each flavor. That seems like a reasonable thing to do, although we do have a controllability problem. If I'm looking, say, I need to test lemon. Well, how do I pick a lemon? Lemon is yellow, but pineapple is also yellow. So can I distinguish between the two in order to pick a pineapple and a lemon? That's a challenge. We might have another criteria, the color criteria for jelly beans. Taste one jelly bean of each color. Well, that's relatively easy to do. I mean, assuming that, the tester has a normal color vision, that's relatively easy to do. It does not necessarily mean that we're going to taste all the flavors. So let's look at some test cases. So I have test case T1. This test case has 3 lemons, 1 lime, 2 mangoes, a banana, a tangerine, and 4 pineapples. That's the set of jelly beans in this test case. So first question, does this test satisfy the flavor criterion? This is a question for you guys, by the way. We got a lemon, a lime, a mango, a banana, a tangerine, pineapple.
Yeah.
I'll go back to the previous one. Lemon, lime, tangerine, mango, pineapple, banana. Seems like, yeah. All right, we've got another test case or another test set. This test set contains a lemon, 2 limes, a banana, and 3 tangerines. Does this satisfy the flavor criterion? No, I see some no's, right? Well, we've left out a couple of things, right? We don't have a mango. We don't have, there must be at least one other thing we don't have. Pineapple. We don't have mango. We don't have pineapple, right? So that does not satisfy the flavor criteria. Does it satisfy the color criteria? Yeah, we've actually satisfied all of our colors. So is one better than the other? Well, maybe they're different. Let's put it that way. They meet different needs. So let's talk for a moment. We'll come back to a comparison between the two, but let's talk for a moment about coverage level. Coverage level, when this is a way that we're going to measure the effectiveness of our test set. And our coverage level is the ratio of the number of test requirements satisfied as compared to the total number of test requirements. So, for example, if my test had 1 lemon, 2 lime, 1 banana, and 3 tangerine, then I've satisfied 4 out of 6 test requirements for the flavor criterion. So I'm 67% is my coverage level for flavor. But I've satisfied 4 out of 4 test requirements for the color criterion. So I'm 100%. I have 100% coverage of the color criterion. So that's how we can measure coverage. This is a useful technique because it tells us, or at least it gives us a good hint of how close we are to being complete, right? We can say, well, I have 4 tests. I'm trying to satisfy flavor. I have 4 tests. There are 6 test requirements. I'm 67%. So I'm most of the way there. I still have some more work to go, but probably not a massive amount of work to go. On the other hand, if I'm trying to satisfy color criterion, oh, I'm 100%. Well, I'm done. I don't need any more test cases. We've satisfied this. So we can compare, right? Those two coverage criteria are different, right? And the same test gives different coverage levels. And we need a different number of tests, perhaps, or different things in the test set to satisfy each of those criteria. So how do those criteria compare? We can compare them with this notion of subsumption. And a test criteria subsumes another one if and only if every set of tests that satisfies the first also satisfies the second. And that has to hold for every possible set of test cases. So flavor subsumes color, because if we test every flavor, then we are guaranteed that we've tested every color. But color does not subsume flavor, because if I've tested every color, I don't know for sure that I've tested every or tasted every flavor. So likewise, if we look at code, if we look at the branch criterion on code, right, achieving branch coverage, if I achieve branch coverage, I'm guaranteed that I've also satisfied statement coverage, because if I executed every branch, I know I've executed every statement. So branch subsumes statement, but statement does not subsume branch. If I test every statement, I am not guaranteed that I've tested every branch. We'll have some examples coming up, I think this week, to talk about why that's true. So what are some advantages of using criteria-based test design? So criteria help us maximize the results that we get for the effort that we spend. They're going to help us build comprehensive test sets, right? Test sets that are as complete as possible with as little overlap between them as possible, right? If I have a lot of tests and those tests mostly do the same thing, why bother, right? I mean, I could probably be more efficient. It takes time and money to write tests, and it takes time and money to maintain tests. So the fewer tests I can use, the fewer tests I can create to do the same amount of coverage, the better. Criteria are also going to give us traceability, right? They're going to help answer the question, why did I need this test? Oh, well, I needed this test because this was the only one that had a pineapple jelly bean in it. Okay, good. I needed a pineapple jelly bean to satisfy flavor criterion. That's why I have this test. They're going to provide us a stopping rule, right? We're going to know when we're done. When my coverage gets to 100%, I'm done. And they're going to give us some idea of how many tests are going to be needed, right? We can get some advanced knowledge of how many tests are going to be needed. And criteria are fairly easy to automate. We can use tools to help us automate these things and help us to understand what the test cases are that we need. That's very attractive. So some characteristics of a good criterion. A criterion. I told you at the beginning of the semester that I mix those words up all the time. Here's another case. No slide correction credit for pointing out where I get criteria and criterion backwards. Sorry, there's just too many cases. But a good test criterion should be easy to compute what the test requirements are. Ideally, automatically, right? It should be automatable. It should be efficient to generate test values. And the resulting tests should reveal as many faults as they can. Those are the things that we would want a test criterion to do for us. And subsumption is a rough approximation of the ability of a criterion to find faults. So flavor testing is probably going to find more faults than color testing. Branch coverage is probably going to find more faults than statement coverage. It's also going to be more expensive. It's going to require more test cases, but it will be better at finding faults. And then I guess I'll just conclude that by saying our job as developers is to pick an appropriate criterion based on what it is we're building. So if we're building some kind of safety critical software, right? Oh, if this breaks, people are going to die. Then we have a much, much, much higher level of testing that we need to do. Whereas if I'm building, you know, a web browser, well, I don't want my users all annoyed, but I mean, no one's going to be hurt if the web browser has a bug. So I can justify a lower level of testing. All right. any questions on kind of our quick test criteria overview? All right, then we're going to dive into our last piece here. We're going to talk a little bit about test doubles. And test doubles, this is what today's exercise is going to be, and it's going to be what assignment 3 is largely about. So why do we want test doubles? Go back to week 1 or maybe week 2. I don't remember. They all run together after a while. We had a case where we had a system, we had some tests or some requirements for our system. If the light is red and the valve is open, then release the monster. If the valve is open and the switch is on, then release the monster. All right, and like I said, this is always, when we talk about releasing monsters, this is the one that comes to mind all the time. Well, there's a problem in doing these tests. The problem being, right, this actually releasing the monster, this could get ugly, right? Our guards get squashed and eaten, and it's hard to get the monster back in the cage again. This is a very difficult, expensive, and possibly dangerous test. So we'll use a test double. We're going to substitute something in for the monster, right? If the light is red and the valve is open, then release the puppy. And if the valve is open and the switch is on, then release the puppy. And yes, this is my puppy, but boy, that was 10 years ago. She's a lot grayer now. This is a much easier to implement test. It's a much less dangerous test. It has very much fewer side effects. We can release the puppy comes out, we give her bone, we pat her on the head, we say, okay, go on back in there now because we want to run the next test. But we can still get the basic functionality that we need, right? So this has all the necessary functionality of testing with the monster without the extra mess and expense. So why do we want to use test doubles? Well, maybe from a software perspective now, maybe part of what I'm testing isn't implemented yet, right? Part of something that I use, right? A dependency of my software. It's not implemented yet, but I want to test my software now. There may be unrecoverable actions that result, or difficult to recover actions that result from using the real thing. We might release the monster. We might send emails to 50,000 customers. We might do a security lockdown of our entire building. We might launch a missile, right? We don't want to do those things in part of in the course of our testing. There might be a dependency that has non-deterministic properties, intermittent failures, intentional randomness. If I'm testing part of a backgammon game, the backgammon game relies on the roll of the dice. The dice roll is supposed to be random. But how am I supposed to write a test for whether my backgammon works correctly if I don't know what the dice roll is going to be? So instead, I'll use a substitute, a test double for the dice that will return numbers in a predictable pattern, and then I can write verifiable tests. There may also be irrelevant changes that happen to some dependency later that may break our tests. Even though my code is working correctly, the thing that I'm calling has changed, which causes me to generate a different answer, and now my test fails. And this is a major source of test maintenance effort. So we would like to have some functionality that looks like the dependencies that we're using without all the mess of using the real one, much like without the mess of using the monster. So we're going to jump down into an example here. It's a little bit of a philosophical example. I'm talking about code, but I'm not actually going to show you a lot of the code. But imagine we have a class called factors. That class has a method in it, get common prime factors. We pass that method two integers, and it finds the prime factors of those two integers. Now I'm going to assume that everybody here knows what prime factors are, right? It's the prime numbers that when multiplied together give us this number that we're using. So this get common prime factors, that's the thing I want to test today, right? That's what I'm writing tests for. But it has a dependency. That dependency is some other class called prime factors. And there's a get prime factors function in that class that returns a list of all the prime factors of an integer. So what's my class going to do? Well, get common prime factors. It's going to take the two numbers you passed in. It's going to call get prime factors to get all the prime factors of the first one, and call it again to get all the prime factors of the second one. And then it's going to review that list, and it's going to find all the ones that are common, and it's going to return that. That's the functionality I want to test. Well, I don't care how get prime factors works. It could be Civ of Aristophanes. Look it up. It could be any number of other ways of computing prime factors. I don't care what it does. I just care that it returns a list of integers. I don't even care really for my testing. I don't even care if it returns prime factors, as long as it returns me a list of integers, because all I want to do is figure out what the common things are between those two lists of integers. So from a UML perspective, it kind of looks like this. This is what I'm testing, get common prime factors. It's making calls to this get prime factors. This is the dependency. I don't care how this works, as long as it gives me back a list of integers so that I can check that this guy works the way I want it to work. So what does get common prime factors look like? It might look like this. This is a possible implementation. So I create a list of integers, I call it common factors, and then I get a list of the prime factors for the first value, and then I get a list of prime factors for the second value, and then I iterate through them, and for each factor in the factors one list, if that is also in the factors two list, then I add it to the common list, and I return that at the end, right? Other implementations are possible. This is an implementation of this functionality. So I don't care how get prime factors works. I don't care if it's correct. I don't even care if it returns primes, as long as it returns something that I can compare.
But I feel, but isn't the case for a lot of software that it does care if it's correct? Because this seems like these testing doubles aren't very useful because in a lot of cases, if you're calling a method, you expect the results of that method to do what it says it does.
At the system level, I agree with you. At the unit testing level, I'm not sure that I really care that much, right? I have to know what kind of thing it returns. And it needs to do something reasonable. But for example, in this, let's look at this particular case. What I'm testing here, when I'm writing tests for get common prime factors, all I care about is that it properly gets the numbers that appear in both of those lists, right? Only return me numbers that appear in both of these lists. Now, I might, if I was testing this with the real dependencies, I'd call it with, let's say, 9 and 12. And the prime factors of 9 are 3, and the prime factors of 12 are 2 and 3. And I would expect it to return 3, because that's the common prime factor. You can use other numbers and make more complex lists of prime factors and get more complex results, but that's a simple result. But do I care how this guy got there? No, I don't really care how it got there. And from the perspective of my tests, like I said, I don't really even care if it's right, as long as I know what it's going to do. Because I have to know what it's going to do in order to write tests to make sure that the results of this are correct. Now, in an ideal world, I'd expect it to do the right thing all the time. But as long as I know what it's going to do, I don't really care if it does the right thing or not. As I move up into more complex testing, yeah, okay, comment in the chat. Is that because we're assuming get prime factors is or will be tested? Exactly. There's going to be some unit tests for get prime factors. This is not that test. This is the test for get common prime factors.
My thing is, in a system, like when I'm working on a system, that this common prime factors, this would actually, all of the time, its functionality would be dependent on get prime factors. doing what it says it does and wouldn't really operate properly with just some arbitrary list of integers.
At the unit test level, if get prime factors gave me back an arbitrary list of integers, as long as I knew what it was going to give me back, I could still write a perfectly appropriate test for this to make sure that what I return is the numbers that show up in both lists. Right? Whether or not they're prime numbers, whether or not they're the right prime factors, as long as I properly return what showed up in both lists, then I work, or rather, this function works. Now, should I go out of my way to do stupid things that aren't realistic? No, that would be a waste of time and would probably confuse people later when they look at it and go, well, why aren't these even prime numbers? That doesn't make sense. But the point is, I don't need get prime factors to necessarily be right. And I'll come back in a minute to why that's important. So let me continue on for a second. So what happens if get prime factors is changed? Maybe to fix a fault, maybe to add some functionality. I don't know, but the get prime factors, it used to return something and now it returns something else. Then my test for get common prime factors, my test is going to fail now. Because it used to be when I passed get prime factors 12, it returned 3 and 4, for example. Now, I know that 3 and 4 is not right because 4 is not a prime. But let's say that at the time I was writing my tests, get prime factors returned 3 and 4 for 12. And I said, well, look, I don't know anything about how that works. I'm just going to accept that as the right answer. So I'm going to build my test around getting that input back. And then somebody comes along and corrects get prime factors. And now it returns 3 and 2. Now all my tests fail, or at least any test that passed in 12, that used 12 as a test value. My tests for get common prime factors are broken. Even though nothing changed for get common prime factors, and there's nothing wrong with get common prime factors, it's working just fine, but something changed underneath it. I don't want the tests for this function to start failing because something changed underneath it. I want the tests for get prime factors. I want those tests to fail if something changes at that level, right? If that dependency changes, I want the dependencies tests to fail, but I don't want my tests to fail. Because imagine you've got some utility that you're using all throughout your system and it appears in like every unit test in the world. And now somebody changes something in that utility and every unit test in the world fails. That's a huge amount of test maintenance to go back and correct those, even though the reason that they're failing had nothing to do with their functionality, right? So we want to isolate failing tests to as low as we can. We want to isolate failing tests to the unit that failed or the unit that was broken or the unit that changed. And anybody that's relying on that, we'd like to insulate them. We'd like to protect them from failures due to problems that happen at a low level. And then we're going to have a lot less test maintenance. So how can we do that? Well, we can use several different types of test doubles. I'm going to talk about 3. We can use test stubs. If I'm using a test stub, that's some custom developed functionality that I wrote. So I wrote my own fake version of get prime factors and I'm using that for my testing. And I link it in or I put it in my class path or whatever language I'm using. And that substitutes for the real one. I don't care how the real one works. I'm not going to implement the sieve of Aristophanes. I'm just going to do something simple that's sufficient for my tests. Great. I might use a mock. A mock is similar, except when I'm using a mock, I'm using some kind of mocking tool, right? Some kind of software support tool to basically automatically provide me with that fake capability. That's really attractive because now I have to write less of my own code, right? Less fake test code. There are lots of other terms in use. You can go online, you can search test doubles, and you'll find people talking about fakes and dummies and spies and lots of other things. Some sources differentiate between what these mean, some don't. So I'm going to stick with stubs and mocks. If you like to use other language, I'm okay with that. And then we can also have a third category, simulators. And a simulator is really a much more complex substitute that's going to have some deep functional capabilities. So instead of just, hey, when you call me, I return 3, a simulator is going to be having some, some deep knowledge of what's happening. So a simulator I'm usually going to use for something much more complex. So if I had a, let's say a thermostat, and the thermostat keeps the control, or keeps the temperature in the room right. I might tie that thermostat in with a simulator, and the simulator will look at what the thermostat's trying to control, and we'll use that to input test data about what the current temperature is, right? It's going to be a kind of a closed loop, continuously operating, much more complex thing. So we're really going to talk about stubs and mocks, and mostly we're going to talk about mocks. So if I want to use a test double, how do I get a test double into my system? So let's look at this example. I've got a JUnit test, and I've got some unit that I'm testing. This is the unit under test. It's commonly abbreviated as UUT. And then there's some dependency that I have. In this case, my dependency is a detonator, and the detonator's job is to make the bomb explode. Well, again, I kind of obviously don't want to do that while I'm doing my unit testing, because blowing up bombs in the lab is messy, really pisses off the lab manager. So we'd like some easier way. So let's have the JUnit test, and let's have the unit under test, but instead of the detonator, let's have some test double for the detonator. And instead of blowing up the bomb, the test double detonator prints out boom. And then I can use that to know that my test did the right thing. So how am I going to get my test double into this test? I have some choices. I could go into my software that I'm testing, and I could write a different version of my software that doesn't include a real detonator. It includes a detonator test double instead. That would work. But then I'm not testing the software that I'm going to be delivering, right? Now I've got multiple versions of this unit under test. That's hard to maintain. If I make changes in one, I have to remember to always make changes in the other. That's not going to last very long. They're going to get out of sync. I'm going to have two totally different things. And the thing that I'm testing is going to get further and further away from the thing that I'm using in the real system. So changing it in code, not a great approach. So let's instead look for some seams. Seams are places where we can insert things, right? Make changes to what's happening. So a seam is just going to be a control point where I can change what the behavior of the software is. And we're going to talk about 4. There may be others, but we're going to talk about 4 different seams. I can maybe use the compiler to change the behavior of the software. I can maybe use my linker or my class path to change the behavior of the software. I might be able to use inheritance and different child classes to change the behavior of my software. Or maybe I can use my Java virtual machine, or more broadly, any interpreter, right? Language, Java or Python, JavaScript, whatever. They've all got a virtual machine or an interpreter. So let's look at a couple of these examples. So if we're looking at compiler seams, how do I change my behavior at the compiler level? Well, I might have some code that's like in a test mode, right? So if we're in test mode, then do something unusual, right? Create me a detonator double instead of a real detonator. Or maybe I have a test mode constructor. Usually this class gets built by calling this constructor, but for testing, I call this other constructor instead. It's got some advantages. It's easy to understand. It's easy to implement, but it's got some disadvantages. I'm not testing the same code that I'm going to be running in my delivered system. And the more compiler changes I have to make, the further and further I get from the thing that I'm really going to deliver. I might look at class path or linker, and I might replace dependency classes with test double classes, either by redirecting the class path. Hey, Java, Java runtime environment, don't look over there for class files that are my dependencies, look over there instead. And that's where I have the fake ones. Or with a C or C++ linker, I could do the same thing, right? I'm going to link in my fake object files instead of the real object files. There are some advantages here, some real good advantages. There's no change to my unit under test. The thing that I'm testing is exactly what I'm going to deliver. This is fairly easy to implement. It doesn't take too much time. It's relatively easy to understand. Although I do have test double classes, right? I've got these test classes over here, and writing and maintaining them might be time consuming. There's maybe the risk that I'm going to use the real one instead of the fake one, or worse, I'm going to use the fake one instead of the real one in my delivered system, right? So there are some risks to doing that, but it's a very reasonable approach. I might be able to use inheritance. So I'm going to derive a new child class of the dependency, and then I'm going to override the functionality with some test functionality. So, for example, I might have a bomb detonator or a bomb detonator interface, and then I'm going to have a subclass of that, bomb detonator test double, and I'm going to override detonate to print out boom. So this has, again, some advantages. There's no change to the class that I'm testing. But it might be hard to insert these alternate classes, right? If my software, if the thing that I'm testing creates a new bomb detonator, how do I get it to create a bomb detonator test double instead? I can use dependency injection to do that. Maybe I can use static class factories, right? There are techniques, but it's a little more complicated to make happen. So let's talk a moment about dependency injection, because this is a pretty common solution. In dependency injection, I'm always going to pass a dependency into my unit under test through a constructor or through the setter method, through a setter method. And I'm probably going to pass in a base class or an interface. So this is really flexible. It allows me to have lots of different types of test stubs. That's very advantageous, but it's got some disadvantages too. It breaks encapsulation. Now my class needs to know about what all of its dependencies are going to be. And in fact, the class that creates my class needs to know about the dependencies in order to pass them in. So I tend to have a need to know about not just my child objects, but also my grandchild objects so that I can pass those in. That can be that can be an inconvenient structure. So what does that look like? So we've got class B. Class B uses some class C. But if I want to use dependency injection, then I probably have to create a base class or an interface for class C. And then it can use either the real class C or a test double for class C. But the problem is I have to pass that in to B. So in my real system, where class A calls class B and class B calls class C, A has to pass C into B. So A has to know about this dependency. Whereas in my test case, my test program can create a test double for C and pass that double into B, and then B can use that test double. Works really well, but this higher level class needs to know more than we'd really ideally like it to know. We also have our fourth approach of virtual machine seams. When I've got a virtual machine, I've got some new options here, right? I can create a mock object, and I can use a mocking framework like JMockit, or JMockit is what I mostly use. Mockito is another one that does this really well. And that's going to automatically cause the Java virtual machine to use the mock object instead of any real dependency. So the JVM is going to intercept all of the calls to the real object. It's going to intercept those calls, and it's going to redirect them to the mock object instead. This is totally transparent to everybody. No change to the unit under test, no dependency injection, no changes to my architecture. It's totally transparent, and the right mocking framework like Mockito or JMockit makes it really easy. There are some disadvantages. The big disadvantage is this only works with Java and with Python and maybe with some other interpreted classes. You can't do this in C or C++. Also, it typically will bring in a single static mock object. So if you have like a dependency and you're relying on there being a whole set of them, well, now there's always going to be just this one, right? So there are some limitations there. All right, so what if we went back to our example and we want to mock get prime factors? What's that going to look like to us? So we've got some class. This class calls factors, get common prime factors, right? That's what we're trying to test, right? We've got a test class for that. And either way, it uses prime factors to get those prime factors of each value. So what's this going to look like? Here's a possible unit test. Now, this is JUnit 4. I have not updated this yet for JUnit 5. I don't know if JUnit 5 is going to look any different. But I'm going to declare with this @mocked notation, I'm going to declare, hey, here's a mock object for prime factors, right? So this mock object is going to pretend that it's the prime factors class. And then I'm going to declare some data for it to return. I'm going to say, hey, I want a list of integers, factors of 4, and that list contains 2. And I want a list of integers that's factors of 6, and that contains 2 and 3. And then I'm going to tell the mock object what it should do. Hey, prime factors mock, I want you to expect to get called and passed in 4. And when you get called and passed in 4, return this list that's factors of 4. And then I expect you to get passed in, I expect you to get called. I expect get prime factors function to be called and passed in 6. And when that happens, return this array that I told, or this list that I told you is factors of 6. So I'm basically telling this mock what I want it to do. The mock doesn't know that it's supposed to find prime factors. It has no idea what the functionality is. It doesn't care. It just knows that you should get called and passed in 4 and then return a list that contains 2. And then you should be called and passed in 6. And when that happens, I want you to return 2 and 3. So going back to the discussion I was having with Kyle earlier, this is what I expect get prime factors to do. I'm not going to kind of purposely make it do something weird. But the point is, I don't really care what the real one does. The real one might not be written yet. I'm putting in this substitute for it that behaves the way I think it should behave. Why all the double curly brackets? That is the notation that is required, and the reason is that I can have more than one of this second double curly bracket, right? So I can have more than this inner curly bracket is a set of expectations. I can have more than one set of expectations. So I can have a comma after this first one and then another whole thing of these. So it's very, very flexible in what it does.
Would there be any like difference with a separate set of expectations? Or is it just for,
in my use, I'm going to presume that there's a good reason to do this because the tool allows it. In my use, I have never done that. So in practice, I have never had multiple sets of expectations. So there's probably a good reason for it. Off the top of my head, I can't give you one based on my experience.
What would happen if you ran the test and also give it a different argument that you haven't given it an expectation for?
Then my test would fail. It would say, oh, you passed me a 7. I didn't expect that. That's not what you told me I should expect. So that's a great unit test capability, right? Because now I'm using my dependency to check the internal behavior of the class that I'm testing. I didn't expect I was going to pass it a 7. I thought I was going to pass it a 4 and a 6. That's interesting. So my test fails. Now I can go back and look at what happened. And if I didn't call this at all, let's say I just made one call. I called prime factors and I passed in 4. I didn't call in 6. At the end of the test will fail because the expectations weren't met. Then I'm going to actually execute the test. I'm going to call get common prime factors. I'm going to pass it a 4 and a 6. I expect that all this stuff should happen. Then I'm going to check the functionality of get common prime factors. I'm going to check that the list has one element and that element is equal to 2, because that's what I expect to come back. So as long as all these things happen, then as far as I'm concerned, get common prime factors is working the way I want it to work. Okay, I got a comment here that I'm looking at where the factors in factors.get common prime factors 4 to 6, where does that come from? Should it be prime factors mock? It doesn't need to be prime factors mock. Here, I think you're talking about here. Shouldn't this be prime factors mock? No, because factors is the class that I'm testing, and factors has this get common prime factors method in it. So this is the call that I'm testing. This guy inside him creates a prime factors object and uses it. But because I did this up here and specified the mock version, the JVM will be on the lookout for any use of the prime factors class and will replace that use with this mock automatically behind the scenes. So my code for get common prime factors doesn't need to do anything different. Just like always, it's going to create a prime factors class, right? An instance of a prime factors class and call it. What it doesn't know is that instead of getting the real one, it got this mock object instead, because the Java virtual machine just kind of grabbed it, right? It intercepted that call and redirected it to the mocking tool. So this is super powerful. The notation is a little weird and you have to get used to it, and it can get very, very complex. But I'm able to test my code with mocks for anything that it might be using without any changes to my code at all. I can take this code and I can move it into integration testing or system testing or delivery without having to make any changes to get common prime factors, because everything is done at the JVM level. All right, so what do I want to use? Do I want to use a stub? Do I want to use a mock? Do I want to use a simulator? What do I pick and why? So if I've got a really, really simple dependency, look, all I need for this to do is to return true. Well, then I could just write a stub, right? I'll just write a stub. The stub says return true. Fine, easy done, easily done. But even then, because I probably now have another test class, right? I've got this fake class. Even then, maybe a mock would be easier because I wouldn't have to write and maintain another class. Now, if I've got a test scenario where I want to verify that my calling expectations are met, and I want to return more complex sequences of values, again, let's go back to that dice roll example. I'm going to roll the dice, but I don't want a random value back, because how do I know if my game simulator does the right thing if the value is random? So I'm going to make a dice mock, and I'm going to tell the dice, expect to be called 10 times and return 3 and then 5 and then 2 and then 1 and then 3 and then 6. That wasn't 10 times, but you know what I mean. Now I can write a test knowing that those are the values that are going to come back. And so I can write a reasonable test. And then if I've got some really complex scenario, like I've got real-time data streams, I've got feedback, you know, what my output is affects what the next input might be, then I probably want a simulator, right? I want to do something much more complex. All right, so all this seams stuff, where did this come from? Largely it came from this book, Working Effectively with Legacy Code. This book is about 20 years old. I do not normally recommend 20-year-old books in a technical field because usually they're obsolete in about 2 years. This book is really the exception. There's a lot of really good information in there about how to think about doing testing, especially how to think about doing testing with legacy code, code that you don't really understand, code that doesn't have good tests, and how do you get tests into there. So definitely worth a read. All right, so that takes us to the end of this. And I know that, wow, there was a lot of stuff in here and not all of it's all that clear. And I think that our best thing to do here is let's take a break. And then we're going to get into our exercise where we're going to try to do some hands-on stuff. And I think that in the act of doing it, a lot of these things are going to become a little more clear. All right, welcome back. We're going to get into our last piece of work for tonight. We're going to do our exercise. All right, so obviously we're relatively short on time tonight compared to most nights where we have kind of more exercise and less lecture. I don't like how all three of these things are packed in tonight, but I don't know where else to put them. So our activity is going to be on test doubles. So assume you're testing a class that does airline reservations. It has a dependency that's a ranking service. And the idea is here that customers with higher ranking, right, more miles, better status, whatever, they get some kind of better arrangements, right? They get the front seats, they get early boarding, they get free drinks, whatever it is they get. We're not testing the ranking service. And you should assume that the ranking service is stochastic, right? It might give different results every time, right? The real ranking service could give different results every time it's called. And that's not the part that we're testing. We're testing the reservation part. So the reservation service might look something like this, right? We've got some class reservation service. It's got a function called reserve. We pass into that the customer. You can assume this is some kind of object that's got data about the customer in it, whatever data that might be. We're going to create a new ranking service, and then we're going to somehow use that ranking service, right, to find out what the customer's rank is, and then we're going to do stuff for the reservation. We're going to book them their seat and get their boarding pass and whatever else. And so there might be some associated test. That test creates a reservation service, and then it creates a fake ranking service, right? We'll assume that this fake ranking service inherits from ranking service, so it is a ranking service. It has that relationship. And then we're ready to do some reservations, and maybe we'll reserve for John Smith and for Jane Doe. And I know that that's a string and not a customer object, but this is just a little bit of shorthand here. So then we're thinking, okay, well, how do I get reserve in the reservation service? Okay, so that slide error. This should say reservation service dot reserve. How do I get the reservation service to use the fake ranking service? That's the challenge that we have tonight. So what if we make ranking service a member variable of the reservation service? And now our reservation service looks like this. We've got a private member, that's the ranking service. And then when we call reserve, we create a new ranking service, and then again, we call it and do things with it. So what else do we need to do, right? We need to think about seams. And so we want to, as our exercise, we want to develop a simple test using the fake ranking service. And I want you to focus on what you want to test, right? Focus on the logic here. Don't worry too much about the JUnit syntax. That's not what I expect you to master in this, in this exercise. And so there are a couple of ways we could do it. And so I have randomly chosen the groups, and I'm going to split you up into different tasks here. So Muggles, the Muggle team, I'd like you to implement this using a compiler seam, right? So you're going to make some kind of change to the code so that you can cause it to use the fake ranking service or the real ranking service. And then Ravenclaws and Gryffindor, I'd like you to use inheritance, but not use dependency injection. Right, so you're not going to pass it in from the parent. So how will you solve that problem? But you can assume that the fake ranking service is a ranking service, and you can rely on that. Slytherin and Hufflepuff, I would like you to use an inheritance seam with dependency injection. And then you could also try, there isn't going to be time, but if you're really feeling like as a group, hey, instead of doing any one of those things, let's try doing it with a mocking framework like JMockit that we looked at, go for it. Or if you have time, go for it. But that's not necessary as part of the assignment tonight. All right, any questions before we go? All right, I'm going to give you 20 minutes. So remember, each team, you're only doing it one way. You're not trying to do it all 3 ways or all 4 ways because there's nowhere near enough time for that. You're just doing it one way. All right, so if there are no questions, I'll send you on your way here. Welcome back. Overall, I think that was probably not among the smoother runs of this year so far. That's okay. I'm trying to find my right presentation here. There we go. Okay, there we go. All right, so I think, I didn't have a chance to circulate around everybody. The groups that I was working with, for the most part, didn't get super far. So I guess I'm going to kind of turn this around right now and say, is there anybody who would like to volunteer to go over what they've got? And if not, then I'll just go over what I've got. Because, there's no point in making anybody, squirm or anything.
Jesse, do you want to go over what we got? I think we were the injection via inheritance. So to do that, you would have to add a constructor that, or a getter, or not a getter. You would add a setter, either a setter or constructor to basically set the ranking service. Just kind of reservation service interface, say the reservation and the fake reservation service would both implement it. I hadn't quite figured out what the...
All right, so you've got a fake reservation service that inherits the reservation service interface. Okay, so you went the interface route. Okay.
Yeah, and it's just a simple set method.
Yeah, and what it does doesn't matter. Yeah. So that's fine.
We're just getting a ranking for it.
Yep.
And then what we did down here is we just created an instance of the test that implements the fake reservation service and a fake, or actually we're using the full ranking service since we're not testing that.
You create a fake reservation service and then you pass it into the ranking service and the constructor, and then you do stuff.
Yeah, so then we set up, it's like a setup method before every test generates a list. So for instance, this list is of customers. So Tom is high priority, Jerry is low, Jeff is medium. And then we pass it the list through a ranking service. So it ranks all the users on there. And then we do like a fake reservation.reserve Jerry.
Yeah.
And he doesn't get to choose a seat.
And then and then you test whatever it is you want to test, which isn't that important here. Okay, so this part looks great. Your test looks great. You're creating that fake reservation service. That fake reservation service is a ranking service. and then you're passing it in.
I guess
Okay, so
actually,
the
actually,
terminology is actually, I'm just catching now. The terminology is actually all backwards here, right? Because you want to be creating a fake ranking service and then using the real reservation
oh,
service.
we might have got. Oh, we might have.
So it's just your first two lines here. I think everything else was right. I think it's just your first two lines here. You just have the types backwards.
You're right. It's
Yeah,
fake.
yeah.
I think we mixed up during the. My bad.
Yeah, no, it's okay. All right, so you're on a good track here. You're on a good track here. All right, let me take over the screen and I will just go
Sure.
through a couple of and thanks for volunteering. I appreciate that because it's this was kind of a hard one, and I appreciate you putting yourself out there and showing off what you had. And like I said, you're generally really on the right track there. All right, so let's look at we're going to use a compiler seam. What does a compiler seam look like? Well, we might have a reservation service constructor, takes a Boolean, is this in test mode or not? And if it is in test mode, then we'll create a fake one. If it's not in test mode, then we'll create a real one. So what would our test look like then? We're just going to create a reservation service and pass in true to put it into test mode. Pretty straightforward, pretty easy to use. Of course, this code gets run when we're testing, and this code gets run when we're in a real thing. And so we're not really testing the real thing, right? When we're running our test, so that's the disadvantage, but pretty straightforward. So if we want to use inheritance without dependency injection, there are a couple of things we could do. But one would be to have, as Kyle mentioned earlier, right, we could have a setter. And that setter is going to override, in this case, we're going to do it set test mode. We're not going to pass anything in, but we're going to tell this thing, hey, go into test mode. And when it goes into test mode, it's going to change its ranking service from what the real thing was, where it went to a ranking service factory and it got a real ranking service. It's going to change to going to the ranking service factory and getting a fake one. Now, there's a lot of assumptions here. I'm assuming that I've built a factory for this class that generates both types, right? So there's a lot of stuff behind the scenes. But now all the rest of the code is the same, no matter what type of ranking service it is. So all I need to do, I create a reservation service, I put it into test mode, and then I do whatever assertions I want to do. So this has a downside, like what if somebody accidentally calls set test mode in the deliverable software, right? Now you've really injected a big problem in your deliverable software. Hopefully it won't happen. Here's another yes, okay, so this is another option without reservation service. I'm going to skip over this one. Without dependency injection, is what I meant to say. This is what it could look like with dependency injection. With dependency injection, I always have a set ranking service. This has to get called. I could have also put this in the constructor, right? This could have been an argument to the constructor. Constructor or setter function, either way is fine. But this has to get called. So whoever's using the reservation service must pass in either a ranking service or a fake ranking service. And we'll crash or malfunction or something if we don't get one or the other. And then what would our test look like? Well, we're going to create a fake ranking service, and then we're going to pass it into the reservation service. Last of all, JMock it. We're basically going to say, okay, I don't need any inheritance, don't need anything like that. I'm just going to say, I'm mocking the ranking service, and I have some expectations. I expect this mocked ranking service to get called with a customer that looks like John Smith. And again, don't worry too much about the syntax here, including the missing parenthesis. And then when that happens, then return 5. Why 5? In this case, it's arbitrary, but 5 is John Smith's rank. And then expect to get called and passed in a customer that corresponds to Jane Doe. And when that happens, return Jane Doe's rank, which is 2. And then what does my test look like? Well, I just create a regular reservation service. And the reservation service creates its own ranking service up here. And normally it would create a real one, but because I've mocked it, it's going to use the fake one instead. And it's just going to happen because the JVM is going to intercept those calls, and it's just going to happen. All right, so we will wrap up with that. I mentioned assignment 3. Assignment 3 is due in 2 weeks. Assignment 3 is basically your opportunity to build this out a little bit and build a set of working tests with a real ranking service and a fake ranking service. It's not that important what it does. I'm really just looking for you to understand the structure of how to use this. If I remember the assignment correctly, I think there was a bonus point in it for using mocking instead of one of the other approaches, or in addition to one of the other approaches, whatever you want to do. But this, basically, you're going to take this example, you're going to build this example out a little bit, and that's the next homework assignment, 2 weeks. All right, anything else before we wrap up tonight?
I have a question on the dependency injection. So my group has a variable ranking service as a ranking service interface instead of the ranking service class. The idea behind that, because we want to use the interface and we did put it the real class afterwards. But I debate that because we actually, when we pass that, we pass it over either the setter or the constructor. So can you correct that or elaborate on that? So instead of having like private ranking service, we have ranking service interface.
Yeah, you could do this one of 2 ways. Right? You have a ranking service. The ranking service does some things. You could either create a fake ranking service that inherits from ranking service. And then you could pass that in, because that fake ranking service is a ranking service, right? It has that is a relationship. Or you could abstract the whole thing a little bit and say, okay, I'm going to make a ranking service interface. This is the set of behaviors that any kind of ranking service has to have. And then I could have multiple kinds of real ranking services and multiple kinds of fake ranking services, and I could pass in whatever one I want. So using an interface is a little more flexible. It gives you more options about having, more things you could do, especially having more different kinds of real ranking services, which is perhaps useful. But using an interface is not necessary, because you could also have a simpler implementation of there's a real ranking service and then there's a fake one that inherits from the real one and overrides the things that it needs to override. Does that answer your question?
Yes, kind of, I think. Yeah.
Okay. If it doesn't, or if you explore that answer and you come up with more questions, let's talk about it in the in the lecture chat forum on Blackboard, so that everybody can benefit from the questions and answers. All right, well then, thank you folks. Have a good night, and I'll see you next week.
Thank you very much for your time, Professor.
Thanks.
All right, good night.